guys. Lesson 39 here. Whew, so close. We are just chugging along. I will say lesson 39, area under the curve, is not going to be a short one-day lesson. So we'll finish 39 this week, today and tomorrow, I hope. We don't need to go to Monday, but it is definitely a longer lesson. It may end up on Monday. But area under a curve. This is really the essence of calculus, and we'll talk about this lesson doesn't really get into what it really is, but I'll give you the secret before I'm done with this lesson. But if we want to find the area under a curve, I'm going to look at a lot of things. There's a lot of words if you want to read along with me. Describe the size of a surface in everyday life. We use the word area. Okay, the area of this table, the area of my carpet, the square footage. We're talking about area. We're painting a wall. We're talking about the area of the wall that we want to cover. Our yard, we're planting seed. We're talking about the area of things, okay? In mathematics, it's helpful to strip away the units, so we're not talking about units this time, and consider area to be a real number that can be used to numerically describe an abstract quality associated with every closed planar geometric figure. This allows us to study numerical aspects of area without having to consider the units that can cause confusion. Okay? For our basic definition of area, we define the area of a rectangle to be length times width. Pretty simple. That's really all we're doing today. And this whole thing is finding the area of a rectangle, length times width. Okay? This definition is used to help find the area of a triangle. Use the area of a triangle to find the area of a trapezoid. So areas are everywhere. We can get one from the other, okay? So on page 204, it's talking about our investigation of areas bounded by curves begins by considering graphs of continuous functions that are everywhere, increasing, and are non-negative on the interval from A to B. Okay, so they draw a shape. They draw a rectangle first. If we wanted to find the area of this, we would go length times width. Okay, and that would give me the area. Okay, if we have a curve on a plane, on the x-axis and on the y-axis, there's a curve, and right now they're limiting it to non-negative, increasing continuous functions over an interval from A to B. So we would look from A to B, and we would want to find the area under this curve. This shaded area is what we are going to be able to find. Okay? Can we prove that such an answer for this area exists? And if it does exist, can a method of finding it precisely be developed? Okay? This lesson concentrates on developing a definition of area under a curve. We begin by finding approximations. So this lesson is not going to talk about that exact, precise number in this lesson, okay? But before we're done, I'll tell you how we can do that in the future, okay? We won't get to it in this book, but it's there if you want to see it. To demonstrate the procedures, by adding the areas of rectangles, we will approximate the area of the region under the graph of y equals x squared plus 1, above the x-axis and between the values of 0 and 2. Okay, so I've drawn a graph. I'll just put this here. So we're going to use what they use, y equals x squared plus 1. Okay, if we wanted to graph that, I'm going to use a different color because we're getting very blue. Our y-intercept is 1. Okay, meaning if x is 0, then y is 1. Well, if x is 1, what is y? 2. If x is 2, because really they're only wanting to go between 0 and 2. If x is 2, that's 4 plus 1, that's 5. So I'm going 1, 3, 4, 5. Okay, so it's this curve right here. Okay, and they just want to find the area between A and B, which they've denoted as 0 to 2. So they want to find the area under this curve. Okay, you see what I'm talking about. So, between A and B, they've denoted 0 and 2. They've given us a function, a curve. Okay, I'm going to go ahead and put between 0 and 2. First, it's always good to have steps. First, we divide the distance between 0 and 4 into intervals. They are going to divide it into 4 intervals of equal length, as shown in this figure. So here we go. I'm going to erase those little dash lines that I have done. I'm going to pretend I'm going to erase them because I realize I did other stuff after. I'll draw stuff back up here if I need to. Yeah, that's going to happen. Okay, so we're going to divide this section between 0 and 2 into 4 equal partitions or pieces. Okay, so I'm going to take 0 to 2 and I'm going to divide it equally into 4 sections. 2, 3, 4. So I have 4 pieces. Each piece is how far or how wide. Yeah, 1.5, and then 1, and then 1.5. Oh, I should have spaced this out more. Okay, but I didn't, so it's okay. So each of my bottom pieces is going to be a half a unit. Okay, they're going to draw vertical lines from the x value that's a half straight up. X value that's 1, or draw that straight up, and the 1.5, going to draw that straight up. 2 I drew earlier because it's the end point. Okay. Now you might have seen also with this title, we talked about, it says in parentheses upper and lower sums. Okay. So the first thing, I'm probably going to duplicate this whole thing and just use it again. Okay, because a lower sum means we're going to underestimate. Our approximation will be less than the area actually is. Okay, but we would take rectangles. I'm going to change colors, and we would draw a rectangle under the curve. And we would draw another rectangle. If we have 4 partitions, we should have 4 areas under, 4 rectangles under the curve. Okay. Now, is this going to be an exact area? No, it's not. So this red is the lower rectangles. Okay? The approximation will be less than the actual area. Okay? The lower rectangles will be less than the actual area, okay? Now, is there a way to find the area of each rectangle? There is. There is. We call this the lower sum, or lower rectangles. Okay? Because we're going to find the area of this first rectangle and add it to the area of the second rectangle, and then add it to the area of the third, and then add it to the area of the fourth rectangles, right? So let's figure out a few things that we know about each rectangle, okay? The first rectangle is always going to hit at the point on the curve, okay? So we can find the point on the curve since we know the formula, correct? The first rectangle, our base is how much? Yeah, it's 1/2. And then what's the height? So I've got base times height. Maybe I'll change colors for this. I've got a lot of red over here. Base times height plus base times height plus base times height plus base times height of each rectangle. Rectangle 1, rectangle 2, rectangle 3, and rectangle 4. Okay? Now, going back, what is the height of this rectangle? Okay? We can see, this one's pretty easy to see that my height is simply 1. But what's another way to get that 1? Okay? Well, I'm hitting the curve at x equals 0, right? So we could put in our base, which is going to be the same, times whatever my f of 1 is. F of 0, because we plugged in 0. Okay? If this is an f of x, we're going to plug in x is 0 and get that point. Okay? It's easy to see in this case that f of 0 is simply 1. Okay? In the next one, what about my base in the next triangle? It's a half again. But what is the height this time? This one's a little bit harder to find. I don't know where it is. Okay? I don't know what's happening there. Okay? I don't know what my y value is. But can I find that out? So it's going to be 1/2 times f of, what's the point? What's our x value going up to? F of 1/2. So what in the world is f of 1/2? Well, I'm plugging in right here into this x. What is f of 1/2? It's going to be 1/2 squared plus 1. What's 1/2 squared? I think it's 1/4 plus 1, which is 1 and 1/4. Or you could say 5/4 if you really want, which we will probably have to change that. Okay? But that is this height right here. Okay? What about my third rectangle? Here we go. We've gone to the third rectangle. I'm kind of doing a few different things. What is my base? Yeah, it's a half. What is my height? I got a 1/2 and my f of what? What point are we at? F of 1. What is f of 1? This one's not that hard. We can almost see that it's coming straight across to be 2. Okay? And now our last rectangle that's going here. Okay, what is my base? It's a half. What is my height? We're going to have 1/2 times f of, where are we at? 1.5. So I'm going back over here. My halves are kind of getting me. What is f of 1.5? Or we might even say 3 halves. Okay? So I'm going to say 3 halves squared plus 1. So 9/4 plus 1, which is 4/4, which is 13/4. Because see, it kind of looks like it might just come out to 3, but it's right over 3. Of course, my drawing's not perfect, so don't just assume that it's 3. You have to plug in your numbers. Because now 13/4 is simply 3 1/4, right? But this one I'm going to go ahead and leave as 13/4 because I'm going to have to go back and multiply them all by half. Now, something you might notice with all of these things that we're adding together, does every term have something in common? I hope you see it. They all have that 1/2. So whatever the base is, since we divided them into equal sections, equal partitions, that distance can be pulled out. We can simply say that's 1/2 of. Okay? And then add all of our pieces together. Actually, I'm just going to scoot it down. 1/2 of. Now, if we look at this little bottom section, it can be written as something kind of like a formula. The base, whatever you've divided it into, will be the same. Times f of 0 plus f of 1/2, because that's what we've divided them into, plus f of 1 plus f of 1.5. Okay? I use brackets in this. So this time our b is 1/2. Our f of 0 is 1. Our f of 1/2, I'm going to go ahead and change that to be 5/4. So I have to add some fractions. 1/2 times 2, that's just 1 again. And then 13/4 times 2 should be 13/8. Oh, I didn't do one. No, it's 13/4 because I'm not multiplying by half. I'm just taking the F of each one. You see what I did? I changed that one. Sorry. I apologize. I changed them. I just meant to take the numbers, these numbers. That's all I wanted, and I changed one of them. I'm sorry. Okay, so if we want to get this area of these red rectangles, the lower sum, we would need to get an answer. So let's go ahead and add all those fractions and numbers. I'm going to scroll just a little. Okay, so I know 1 plus 2 is 3. 5/4 plus 13/4, 19/4. Of course, you wouldn't be something nice. 3 plus 19/4. So I'm probably going to go ahead and change that 3 into 12/4 plus 19/4. 12 plus 19 is 31/4. Whew. So what is a half of 31/4? I don't know. It looks like 31/8 to me. And guess what? That's exactly what they're going to say. Why did I write 38? 31/8. Okay? So my lower sum is equal to 31/8. If I did my math right, we're going to go back and see. Oh, they give it in decimals. Why would they do that to me? 31/8. Somewhere I have a calculator. 31 divided by 8. Let's see, did I do it correctly? 3.875. Oh, they have 3.75. Somewhere I have a decimal off. What happened to me? You guys are watching from home thinking, oh yeah, you messed that up. 4 5/4. That's just 2. My 13/4 could be wrong. Yeah, 13 plus 5 is 18, not 19. Of course, why does that happen to me? Because you're not here to help me. To say 5 plus 13 is 18. So that should have been 18 here, so that would be 30. 4, so 38. So 30 divided by 8, yep, is to 3.75. Now, I need you guys here to help me keep things straight. Go back. 38, which is equal to 3.75. So that's my lower sum. I'm going to go to the next page and do an upper sum. Okay? Lower sum, the rectangles are below the shape. Guess what's going to happen in the upper sum? Yep, you're right. They're going to be above. It's going to be above it. I'm going to make my grid be bigger. I wonder if I can do that. I forget how to do it. I know I've done it. Yeah, there we go. I don't want to go too big. How about that? That just made them be larger squares, ultimately. So I'm going to start down here. And I'm going to start over here. Why haven't I done that before? Okay, so we have the graph. Y equals x squared plus 1. So we were at 0 to 2. We plugged in 1. Y equals x squared plus 1. And we were in the partition on the interval 0 to 2. So if I plug in 2, I got 5. 1, 2, 3, 4. 5 is here. Okay, there we go. We're trying to find the area under this curve. Okay? So now with the upper sum, our rectangles are above. Okay? So here we go. We're still going to do 4 partitions, 4 equal partitions. Okay, so I'm going to a half and 1 1/2. Okay, so when we draw these lines straight up, I'll hit H1. Okay, we already know that's not 3, so don't get excited. When we are drawing the upper sums, we're going to take the rectangles on the outside. So we're starting from the left and going outside. Okay? We're going to start here. We're going to go out, and then this will be our second rectangle. Our third rectangle will be here. This time, our fourth rectangle, we're actually going to use this line at the end. So that will be our fourth rectangle. Okay? So our rectangles are outside. So and they're above it. So it will be, the approximation will be more than the actual area. Okay? So let's go and look at our first rectangle. Okay? I'm going to go ahead and pull out the base. Okay? Because we know the base is going to be 1/2. It's going to be 1/2 times the height. 1/2 times the height. 1/2 times the height. 1/2 times the height. Okay? We just need to know what height are we using. Okay? When we're using the upper sums, we will not use 0 like we did with the lower sum. If you look back and look at the lower sum, we didn't use the last 0.2, did we? But with the upper sum, we will use the 2 and not the 0. Okay, does that make sense? So here we go. I'm going to write it the formula way. The base times f of, this time we're going to start because our height is at f of 1/2. Okay, plus the next one, our height is going to be f of 1. Plus f of, what's the next one's height? We're going up to 1/2, 1.5. And the last rectangle, we're going to use this 2. We're going to look at f of 2. That will be the height or the y value of these rectangles. Okay? Whew. So let's look. I know we've already done some of these. So let's look at f of 1/2. When we plug in 1/2, 1/2 squared, what that's right, was 1/4 plus 1. So we ended this piece. We got 5/4. Correct? So we'll have 1/2 times all this. Plus, what's f of 1? If we plug in 1, we simply get 2. F of 1.5. If you look back, I think we got 13/4. But we can try it again. We can do it. So if I do 1.5, so 3/2 squared plus 1, 9/4 plus 4/4. Yep, that was 13/4. Plus, now we are using f of 2. So going up to 2, if I plug in 2 squared plus 1, we're going to get 5, which we already had that one figured out. Okay? So now 5/4 plus 3/4, now I know is 18/4. Plus 2 plus 5, which is 7. 7 is going to be what? 28/4. Yeah. Times 1/2. 18 plus 28 is 46/4. Times 1/2 is 46/8. So I'm plugging that because I like fractions better than I like decimals. This is weird that they do it in decimals. So what is 46 divided by 8? Let's see, did I get it correct? 5.75, yes! So my area, my upper sum area is, I'm scrolling just a little, so bigger boxes, I think I write bigger. Upper sum area is equal to 46 over 8, which is equal to 5.75. Okay? So we could say that the area under this curve is between the upper and lower sum. So the area is between, because we're just finding approximations right now, the lower and upper sums. So it has to be between, what was that last one, 3.75? Yep, 3.75 is less than the area and is less than 5.75. So the area between them will be between these two numbers. Okay? Whew, I feel like that was a lot. The actual area will be between that. That was a lot. We'll do more. There's more to do. You're good. We're not going to have any homework tonight. I'll talk to you later. Bye.